So thank you for coming. Good afternoon. It's for me a great pleasure to introduce to you Professor Michael Kohlhase. He's a professor at our university in computer science. His broad field of interest is knowledge management, and his talk will be precisely about how mathematics and computer science interact, but maybe not in the way we are used to, right? We are used to think on computers as probably support machines in order to help us on computer-assisted proofs. But I think Michael will tell us about another dimension, right? So, and we are very glad that he accepted to deliver this talk. We try to promote this series of MoD lectures initiated by the Center Mathematics of Data that the university launched, and well, other than those that are, were willing to come here in a dark afternoon, probably also some other people will be with us online, and you are all very welcome. So thank you, Michael, and it's
thank you.
Your time.
So let me first disclose that I'm basically, by early training, genetically predisposed towards math. Math is the first academic love in my life. And but then at some point I got hooked on AI, which with what I mean not machine learning, but symbolic AI, or as other people say, good old-fashioned AI, also termed GoFi. Right? So, and what I want to tell you about today, you're supposed to react. Well, okay. React not at all. That's interesting. No, there it does. And I like to start my talks with a conclusion. For two reasons. One is I sometimes run out of time. When I give you the conclusion up front, then after this slide, the talk is finished formally, and I cannot run out of time. And you probably can ask questions, which is at least as important as getting through the slides somehow. That's why you're seeing the conclusion slide at the beginning. And what I want to tell you about, and what the conclusion actually talks is about, formalized mathematics. And formalized mathematics is a topic that has been going on for 60, 70 years by now, almost 70, and mostly unnoticed by mathematicians. And what we do is we express the mathematical knowledge in logic. And then we use sophisticated software systems like that we call proof systems that actually verify or computer support our management of this mathematical knowledge. In particular, check proofs. We have what we call a calculus, a logical system, comes with a way of making proofs. And it's so explicit that a machine can actually check it and at the end say, yeah, we have a proof. And then we really do have a proof. It doesn't have any gaps because the proof assistant checker is done. It doesn't fill any gap. It doesn't want to fill any gaps like we as mathematicians do, right? We never write down the whole proof. We always leave out details because, well, our readers can reconstruct them. Well, except sometimes there isn't really a proof gap to be filled. It's just a mistake. And proof assistants are very, very meticulous about this. So if a proof assistant says, we have a proof, we actually do have a proof. It's gory detail. It may be a terabyte long, the proof. Nobody will want to read it, and it's difficult to learn anything from it, but we have a proof. It's a certificate, much less than what we as mathematicians think of as a proof, which is a conversational piece made for convincing others of the truth of something and showing them the nice techniques I've invented in the course of this. And we also make modular libraries of reusable mathematical components in the process. That's kind of what I was tasked to do. I mentioned formalized mathematics in a meeting, and I got to, oh, you have to give us a talk about it. This sounds nice, and that's kind of the thing I'm supposed to deliver. It's not really what I do in my research. In my research, in my group, we try to get around the problems that this makes. And one of the things that we're going to see is that full formalization of proofs is extremely, extremely tedious. And you don't really want to do it, but there's a heavyweight method. They give you full truth assurance. But there's not really anything wrong with peer review. Thank you very much. If there is an error, it will be found. Or the paper is irrelevant anyway, then nobody reads it and nobody finds the bugs, but nobody cares about the bugs either. So I would like to show you, if we have time and you're not asking so many questions, to show you a couple of more lightweight things like formula search and how one could do that, or taking LaTeX papers and extracting semantics out of those. And I think of those as not fully formal, but maths doing flexible formality. And if we have time, there's another facet of this where instead of talking about one logic for what theorem prover, we kind of try to connect all of them and all of those kind of things. I have the suspicion that we won't have time for that, but that's fine, because there's lots of stuff that we're also doing that I don't even have prepared. No, I don't brought slides for. We're interested actually in mathematical data, but much different than the mod people. We're really thinking of math as data, as the data. We do things like the Open Encyclopedia of Integer Sequence, which you may have seen, which has 350,000 and counting integer sequences like the Fibonacci numbers and knowledge about that. A rich, rich, rich set of data about mathematical objects. There's the LMFDB, you may have heard about it, something similar in number theories, basically terabytes of examples for elliptic functions and so on. We have our own little system. I should have really given the talk about that, but I don't, because I have to tell you about formalized mathematics. We're looking into linguistics of mathematics. We're using all of those things in AI-supported teachings. That's we have a big project on that, and we're having oodles of fun with that. And all we do in symbolic AI, rather than in machine learning, is things where truth and certainty are very, very important. In math, obviously, rigor is important. We want to be absolutely sure that something is true. That's why we use proof. In legal reasoning, we better be sure about our reasoning there as well. I'm kind of worried about what happens in China, where we have machine learning based courts that actually send you to jail for something they've learned from data. We're trying the symbolic way here. And that kind of ties back to what I do, namely knowledge management. Knowledge management with symbolic AI methods works well if we don't have a lot of data, because otherwise other people can do it better via machine learning, and where high precision is actually needed. Which is why math is such a wonderful topic, because we know exactly what we're talking about. It's not like literary studies, or human relationships, or global economy, where nobody knows what they're talking about. I'm not, please don't put this into the protocol, but that's my impression. In math, we know what we're talking about. Things are totally clearly true or false, and that's heaven for anybody who does symbolic math. Okay. Now the talk is officially over. You can ask questions. You don't have a little bit more material.
Well, so I'm curious to what is artificial intelligence support the math teaching, but maybe this will be a long discussion, right?
Yes.
Maybe you can say just a sentence.
I will say just a sentence. The idea there is to symbolically annotate all learning materials such that we can do things like generate personalized teaching materials. You can click on any word, any content word in my slides, and it will generate a tailored to you explanation for you. It's really quite cool. Symbolic AI. I'll show you.
But is this, for instance, in your slides? Is the case you can
in some of my slides, not the ones I made this morning at 5:30. Because there's quite an investment in it.
Okay. So
but if you come to my AI lecture, you will see that all of the content words are actually colored, and you can click on any of them.
Michael, may I ask a question? My dear, say, once the proof checker has gone through, the proof is absolutely true, right? If there is no gap, right? What is, the simple and stupid question, however, that people might want to ask, nevertheless, the machine has a physical reality. I mean, it's about currents flowing in the network of the computer. So how can one be sure that this thing works?
You can't. Also, this is being, the machine is actually being programmed by humans, and they make errors. But we've developed a proof that's an object, a digital object, which is so explicit that it can be checked in linear time. And we'll just do what the ancient Jews did when they had to translate, the Bible from Aramaic to Greek so that anybody could still read it. And they were worried about whether this is still, after translation, the word of God. What they did was they asked 300 individuals, locked them up in little sheds, and they couldn't talk to each other. And all 300 translated the Bible, and they compared all 300's ones word by word, and it was word by word perfect. So it must be the word of God. We can always do this. We can let somebody program a checker that's about this much code in Prolog, and one in C++ and one in Java, and we lock them up in sheds. And if all of those say this is a proof, then that's fine. There's a lot of work in developing the proof with the machine. The checking is actually linear time, not a problem. Good question. That's why we insist on having these immense proof objects, because they're so big that they have so little left to the imagination that even a stupid Prolog program can actually do this. Any more questions? And if a cosmic ray comes in and one of them flips a bit, we can just run that again and see whether it comes up without the flip. Yes?
Can you maybe expand a bit on how expensive or how difficult it is to convert, let's say, any kind of mathematical statement to something which you can actually then, with your formula methods, and check for a proof?
Yes, that's exactly what I want to do now. Thank you. That I've basically said. Math is really interesting for people who do formalization because we know what we're talking about. Math is very diverse in what it does. It's very sophisticated in structure. That's something we like. The structure is very, very overt. If something is a definition colon 3.7.1 is written in front of it. If the proof is at an end, we make a little box. All of those things are really wonderful. And really what we're after is, how do we do math in the 21st century? And before I go into this, I would like to mention Bruno Buchberger from Linz, one of my scientific heroes and mentors. And he said, well, if we make math formalized, then it's accessible to the computer without meaning loss. That means the whole process of doing math, which at least has things like concept formation, making hypotheses, computation, theory explanation, experimentation and testing and all of those things, can be transferred, at least in part, to machines. And if we do it right, and we get the meaning right, and we have everything formal, we don't have to kind of get a conjecture out of my conjecture helper, have to retype it in Mathematica, to compute with it, right? We can actually harness up all these machines into what we now would think of as a virtual research environment. And the spiral thing here says good things happen then. Right. So formalized math is kind of the computer science take on mathematics. How would we do mathematics if we were doing it by computer? And really in AI, doing math on the computer has been one of the kind of Drosophilas which you can study on, because if we can do math well on a computer, everybody will believe us that we have intelligence. Right? It's just like chess playing, if and go and so on, right? So even the first AI program in the world, 1956, was a theorem prover. It was essentially a theorem prover for Pressburger arithmetic, which is a small part of arithmetic, and it actually Christmas 56. I want to give you a little bit of a history of what formalized mathematics does. We have something that kind of for the mathematics community looked like formalized mathematics, which is the four-color theorem. Let me remind you, it's basically a 300 to 400 page proof that reduced the infinitude of graph maps into a finite number. I think it was 1800 something, which were then checked by computer, and that gave a big controversy. Was this really a proof or not? And they kind of found their peace with it. So checking finally many cases by a computer was kind of counted as an irrelevant part of the proof, so it was accepted as proof, the 300 pages. They were checked by a special built computer program, which ran for over 1,000 hours. That's, for anybody who wants to do the math, is 40 days, which was immense by the time. And there was a special issue of the journal that had kind of all of these graphs as microfiches in the back. I still remember that. In 1996, the first automated theorem prover, EQP, proved a conjecture that had been open for 50 years, the Robbins conjecture, something that even Tarski had dabbled with but not proved it. And I would like to show you how this looks. We write it down in logic. Something of the form n of n of n of y plus x plus something or the other is s, and then we have things like the Winker condition and so on. There are two of those, and if you deny them, then you can prove by showing that this is impossible. And what we see on the left-hand side is we tell the theorem prover in what mode it's supposed to run, and then you press the button and say run, and then the theorem prover kind of goes away for a week. This particular theorem prover, before it found its proof, it examined I think 3 billion formulae, and in the end it came back with this very small proof. But you can see you have to do kind of detailed, big expansion before it gets better. Okay, this is not something humans are very good at, and it actually goes on a little bit here on the end. But this is indeed a proof. It's machine checked. It's actually machine generated. All the human had to do was to write this down, which is fairly easy. Here, formalization is not a problem. To get those right, you had to be Bill McKeown at the time, because he had kind of this notion of how to steer this theorem prover, and it came up with a proof. So this is something the humans couldn't prove, or wouldn't spend enough time on to come up with these weird expansions, and then then the machine did it. And this is something we still do. And we're mostly with automated theorem proving, not proving conjectures, mathematical conjectures. That was kind of a fluke of luck. We are proving what we call junk theorems. All the little things that kind of, in terms of reasoning, come up like 1,000 a second, we can actually prove 1,000 a second. These automated theorem provers are enormously fast. They can do what you can do in 5-6 minutes. They can do in 10 milliseconds, and not even develop a headache with it. But if it's something that you need half an hour, it runs forever. But they're being used quite a lot in many kind of under the hood tasks. 2005, two of my colleagues machine verified in a system called COC the four-color theorem, namely the 300 pages of math proof that led to the 1,800 or so things. And that is something we call interactive proof, where we as humans formalize all the lemmata and all the knowledge that leads up to such a proof. The lemmata, we actually formalize the proofs as well. What is the sequence of arguments? Then we call a proof assistant, a system that checks this and actually tries to close all the gaps. And it's medium dumb. The gaps are still smaller, essentially, than what a mathematician would leave. But if you would kind of give something in full detail, then you would be somewhere near there. As a factor of 2, 3, 4 or so in length. But and we have to make choices here that mathematicians don't have to make, because mathematical language is much more flexible than the language of logic. We don't really have to say, is this a function of one argument, right? We have a whole family of functions, f sub a of x or something like this, and then we don't really have to say whether it's a function of a with parameter a, a function of x with parameter a, but we can just turn around and make the derivative but in direction a. Not a problem. That's not something you can do in logic. That has the added safety, but it also has the added tedium that you can't just turn around and do the derivative in the direction of a, right? And so interactive proof is tedious. This was a PhD level for 2 people proof, which means something like 6 person years. In the next 10 years, we've seen 2 other big verifications. Again, Georges Gontier verifies the Feit-Thompson theorem, which is kind of one of the, they say, foothills in the mountains of the classification of the finite simple groups. And it's something like a 30-person year team effort, which actually much clarified the math behind this proof, because we had to. And sometimes the math as written down was so tedious to prove that they just invented better math and kind of fed it back in. Tom Hales has verified his proof of the Kepler conjecture, which hadn't been accepted, and that's also about 30-person year task. He couldn't get his proof accepted by the mathematical community, so he got so mad because it had lots of Mathematica and so on computations in it, and that nobody said they could verify that they could actually peer review the paper. So he got so mad that he said, "I'm going to do it in a prover," and indeed he did after something like 10 years, where he had recruited lots of Vietnamese students because he was on a sabbatical there, and they got interested in this, and he had a whole army of people. And he used two theorem provers, Whole-Light and Isabel. Right. 2021, there was this liquid tensor experiment where Peter Scholze from Bonn had developed something, and he wasn't quite sure what it was. He basically says it could have been, maybe I spent a year on complete nonsense, and he was so unsure of the whole thing, he didn't want to even give it to his colleagues for checking. So what he did instead is he got together with the Lean team. Lean is one of the newer theorem provers, and they just basically formalized the whole thing, which meant there's something of value there. They were able to verify his theorem. So that was probably the first time that that theorem proving actually gave something to mathematics. It gave Peter Scholze a lot of peace of mind. So much indeed that the math department in Bonn advertised 2 professorships on formalized mathematics the next year. Well, this year, Kevin Buzzard, who's been involved in the liquid tensor experiment, got a big grant, 5 years, I think, to formalize Weil's proof of Fermat's last theorem. That's ongoing. And the Hausdorff Institute avoided the community a special trimester in Bonn. I'm organizing that. I'm just in the process of deciding who of all of my friends comes for 4 months to Bonn, and we're going to try and develop this. It's kind of a potted history of formalized mathematics. So to answer your question, if it's a bigger or a meaningful mathematical theorem, don't be scared if it takes 30-person years. But there's a payback. If the math gets better, more succinct, more stable, more generalizable, if you like these things. Okay, you have kind of a, and we're doing a lot of work in putting a lot of work into making the logics more readable. But the early things from the 96, you could almost not read what's there. Today it's much better. Unicode helps, and MathML and so on helps. And so we're putting a lot of work into this because humans have to somehow survive doing these ginormous proofs. That takes something to it. Now, we've seen 3 or 4, 5 maybe, big theorem proofs. So it's not quite all of math yet. And if you think about it, if you think about what math knowledge is, and then we'll see that not all of it is printed. There's lots of stuff on blackboards or in YouTube videos or so. Some of it is printed for archival purposes. That's actually nice. We can OCR that and digitize it. About 50% of math has been digitized. Probably now, I know. That was 10 years ago when I made the slides. So maybe 60% by now. But digitized means actually TIFFs, means pictures of it. This is wonderful. If you think from a service point of view, you can actually get it to your screen without having to go and see the original in Paris or something like this. This is nice, but it's not quite knowledge management. So we distinguish that from what we call presentational, where we have actual letters and actual symbols, and they can be kind of distinguished, and possibly even, if you're blind, read to you. Right? That's another level of digitization. And finally, semantic, which is really functionally marked up so that we can feed it to a theorem prover, maybe. Unfortunately, this is my guess. We only have very, very, very little of that. Okay? It would be nice to have lots more, and I'm going to show you some of that. I'm going to skip over all of this. This is
So can I just have a
Sure.
question? So last year or so, there was this development by Open AI
Yes.
about a new way of multiplying big matrices using artificial intelligence and reinforcement learning and so on. So is this something that is totally away from?
totally away. That's machine learning stuff with all of its advantages and disadvantages, right? It's coverage is much higher, but precision is lower, typically. We don't quite know what GPT and so on can actually do, but precision doesn't seem to be, or at least precision for larger tracks of development, it doesn't seem to be one of the things where it excels. Whereas precision is the name of the game for symbolic AI. So that's really what we're doing. We're writing down things in logic, which is so easy, we can build machine checkers for it. We know exactly what they're doing. And with GPT, we have to resort to social science methods to find out what it's doing at all. And so the things we're really being done with formalization is we're really interested in actually doing it, which is very tedious. So one of the key factors in this, what we call the de Bruijn factor, is basically if you look at the formalization, how much longer is it than the original? And the interesting thing is if you formalize whole books, the de Bruijn factor at the beginning is about as high as in the end. So that gives us hope. Another thing I want to basically say a couple of words about is I've basically given you this picture of big proofs, right? We have the big proof of the theorem. Think of that here. And we have a ginormous proof. And that's misleading. It's not true. What we're really doing is we're building big libraries of intermediate results. And the big proof is kind of the snow cap, the ice cap, whereas the library is what we're really developing. So to give you some sense of the state of the game is if you look at, there's a couple of libraries. The lean MATLAB 4 is really where most mathematicians flock to at the moment as the theorem prover, which is mostly because they have one extremely dedicated, talented person who mans the chat, the Zulip chat, and whenever a mathematician has a question, no matter what time, he answers with an extension of the system within 4 hours. So that's really attractive. And the lean MATLAB 4, which is the 4th version, they are all re-implemented for every sim, is we have 350,000 statements, definitions, theorems, proofs in there. We have the Coq library, Coq library for the Coq theorem prover, a French thing, which uses constructive type theory to get constructive proofs out of it. They have about 300,000 statements. It's not quite clear they have this distributed library where nobody knows where the whole stuff is. There's a German-British theorem prover called Isabel. They have something like, they have the Archive of Formal Proof, which is very well maintained, which has 250,000. We have a Polish offering in set theory, based on set theory, which has 100,000. They're working since the for the last 60 years on this, a bunch of crazy logicians, topologists, and so on. And we have a couple of others, which is about, you think about, there's 120,000 pure math papers a year, and we have probably 1 million theorems in these libraries. Then you can see that something like 1 per mil might be around the right ballpark. The problem with these is that we have that all of those are logical silos, meaning they all have a different logic: constructive type theory, set theory, higher order logic with refinement types, and so on, which are all good for something and make the systems better at something than other systems, but they're all non-interoperable. We cannot yet actually take a whole light proof and transform it into an Isabelle proof. Right? It's basically like if French mathematicians couldn't speak to German mathematicians because French and German is incompatible. In math, the wonderful thing is you can translate. It's not a big problem. In these logics, it's a big problem. And so that's one of our big problems, and we're trying to do something about it. So, there's my conclusion again, because I've basically given you what I was supposed to talk about. I think I'm almost up with my time. So I would like to briefly give you 2 more glimpses. And I'm going to do that not in terms of slides, but I want to show you 2 systems.
So why if everything is completely logical, translations is not possible then?
Because, for instance, the calculi have different epistemological things. So the constructive people do not accept the law of excluded middle, which makes many of the math proofs much harder. But some of them you can actually prove. It's just 10 times as difficult. For instance, the fundamental theorem of calculus, which is a relatively simple thing to prove in a classical setting, becomes enormous, but still true in a constructive setting. And some of these people say, well, but isn't it nice if I can take any mathematical proof and extract a program that computes me the respective witness out of it? That's what math should be. Well, and then there's things like Mizar that says, no. Math is first order logic with Tarski-Grothendieck set theory in it. And that's what we're going to do. And then people like Isabelle say, no, you don't really have a notion of function there. We have to have a logic where functions are basic, but we do not need constructivity. And all of those systems have good reasons why they're doing what they're doing, but that makes them incompatible. And for math, where we don't really insist on only doing inconstructive or constructive proofs, but we say, well, look, we're doing this non-constructively, and it wouldn't work constructively. Think of that in a partial, in a relative clause. Or we say, oh, note, we use the axiom, we use Son's lemma here, be careful. Right? In a system that does not supply Son's lemma, you might be in trouble here. For good reason, because those people do not want to rely on the axiom of choice. So these systems are much less flexible, which allows them to be machine checkable, but we lose flexibility. So at the beginning, we were taught to frown at mathematicians. They think they're rigorous, but well, look at all the things they're doing. I basically have the feeling that mathematical language is just a wonderfully engineered tool that allows us to flexibly do things while not being completely arbitrary in what it might mean. And it's enormously well engineered towards communication between humans. But we're seeing all these math projects that kind of become very, very big. If you think of the classification of the finite simple groups, right? That's something, if you kind of collect all the papers together, it's an undertaking of 50,000 pages. They don't quite all fit together, and nobody understands the entirety of this. So what we're seeing there is we're seeing these projects that get so big that they're too big for a single brain. I think of this as the one brain barrier. Math is kind of always skirting along the one brain barrier. And it doesn't help of being 10 people, because then you spend all this time only on teaching each other something. Math is in the danger of kind of banging against this one brain barrier glass ceiling. And I think the only way of doing something about it is to have math knowledge as data and enlist machine support. And formalization, or flexi-formalization, which I have told you nothing about yet, is, I think, the way to go here. And if even Peter Scholze has developed something for a year and then is unsure of whether it means anything, right, that you're banging against the one brain barrier there, right? And that's where these machines can actually help you. And I've looked at the kind of the proof aspect of this, but we have a lot more other things, right? Just finding the one theorem that gets me unstuck in a proof is something we humans are really bad at. Right? There's 120,000 papers. Nobody knows all of this. And Google can't help you. Google can help you if you know the name of the theorem, then you can find it. But if you don't know you kind of know the shape of the results, then there's nothing you can do unless you have a formula search. Let me show you one that we built just as a little teaser. Centralblatt runs it, or one instant of it. And let me just hit an example, then I cannot actually do anything wrong. If we want to look at this formula, kind of inspired by Fermat's theorem, but the red parts are actually wildcards. We're looking for a formula that is of the form a to the n plus b to the n plus c to the n, where the n is always the same. Well, let's ask the search engine, and I hope it's working today. Yes, we have a couple of, I'll take one of, I don't want to see the author, I want to see this. Oh, the title has it, right? an to the x plus bn to the x plus cn to the z, right? Ah, no, that's not it. But here, this is where we found it. Okay, we can search for mathematical formulae, and we can do so for large collections of math. So the other thing I still want to show you before I go off, you're probably all familiar with the archive, because that's where you get much of your math papers from, but you get them as PDF, right? Well, there is an alternative. No, that's not the alternative. If you just go from, instead of archive.org, which gives you PDF, you go to r5.org, which gives you HTML5, we are translating all of the archive into HTML plus MathML. So here you have a simple paper. The thing you're not, the thing you can't do with the PDF is read it on your smartphone, right? And it reflows, and all the formulae are there. And our server just died, but we have a search engine running over all of the archive. There's a couple of giga formulae in there, and we can search over them in the way I showed you. And you can find all the formulae there. And then you can get possibly unstuck if you know the shape of the material. Oh yes, and by this is something which is really hosted at archive.org, but it's made at FAU, okay? And at NIST. A PhD student of mine does this. If you ever read a paper which has this funny 7-digit number or something like that, you just change for the paper URL the archive.org to r5.org, and you get the same paper. In MathML, you can read it on your smartphone on the beach if you have connectivity. And we're having a lot of fun with these kind of things. And we're doing math linguistics on this wonderful corpus. And the theme is math as data, which is why I'm in the MoD center to kind of say, but there's also another way. Good, that's it.
I am pleased to introduce to you Edriss Titi. You probably all know his name. He is a professor in Cambridge and also in Texas A&M in College Station, and also in Wilson Institute in Israel. He's a well-known expert in particularly in Navier-Stokes equations and fluid dynamics in finite-dimensional dynamical systems. And today he's lecturing on nudging and data assimilation for climate prediction, which is again, of course, an important and classical topic. Although here in Erlangen in the winter is very easy to predict, right? So it's cloudy almost every day. But thank you for accepting our
almost
invitation.
every day.
Almost.
So that's not prediction.
One exception every 10 days or so. Yeah.
So that's prediction.
Yeah.
Thank you very much, Enrique, for the invitation, and thank you for coming. So, all right. So I'm going to talk about data assimilation for weather prediction or for climate prediction. Of course, I'm not going to go into the climate models, etc. I'm going to talk about prototype, but they're just to fix ideas. But let us start from what is the question that how to make weather forecast. So what people do in general, give you what's the picture, and then I seek to adapt it maybe, but maybe adjust it in order to fit because I would like to prove theorems. So what happens here is the following. Suppose you have an equation which is, say, it controls or governs the motion of the climate of the atmosphere. The u dt equals f of tu, which is a functional equation in infinite-dimensional spaces, where u is the unknown variables representing the state of the atmosphere, say velocity, field, temperature, moisture. So this is the evolution. And now, if you have a super great computer and you give me the initial value, then I assume that I can compute, then I can integrate, and therefore I can find the solution. What happens is that I don't have the initial value usually. That's the problem. And therefore, the whole problem is we need some data to recover the initial data as accurate as possible. And then when you recover this initial data as accurate as possible, you can integrate it. But of course, this is chaotic dynamical system, and we know from chaos theory, small error in initial data, because even if I try to get the initial data as accurate as possible, when I approximate, there is some error. I can predict that for a short time. That's why you can predict the weather only for a short time, even if you have like as accurate as possible the initial value. But at the moment, my mission is to recover the initial data as accurate as possible. from information in the past, from information that I collect about the weather, like weather stations, satellites, etc. So the question is, how do people do? Now, as I said, I want to know the initial data. Unfortunately, the way I'm going to formulate it mathematically is that I'm going to find the solution at time t, and capital T is my zero. So I have to know information from the past because I have data from the past, and then capital T is, the way I formulate it is I started from zero and collecting data at capital T, okay? So capital T is zero, think about it, and zero is like minus T if you want from the past. So what happens? How people do? So we have observational measurements, okay? So you have some observational measurements, and then what do? You have some kind of like background model. This is the background model. You take you integrate. But then when you get to here, you compare your solution with the observation, and you find that the solution, because you predicted initial data, or you guessed an initial data, the observation does not match very well the solution that you find. So you need to do some massaging, okay, some engineering. You would like to basically take the solution that you get and you do some analysis and adjust. So this is the observation. They don't really fit nicely. So you have to do something, because I cannot continue from this as the next step initial data. I do some analysis, I get an X, and I'll take this X as initial value. I run this system, I integrate forward, and then I get a new solution. Then I have observation, I compare, I do the analysis, and I compare. That's what people do. And then they continue until at the end, basically, they say, well, this is the initial data as accurate as possible I can do it. So there are steps. You guess initial data, you integrate, you compare with the observations, you do some hocus pocus, you do some massaging, you add some, you cooking, you taste the dish, does not taste good, you add some more pepper, some more this. That's the analysis part. You integrate a little bit, you cook a little bit, you taste, it does not fit, you add some more until you basically are happy with the dish. That's basically what people do in principle. I would like to basically tell you this analysis part, or what we would be doing, and how to try to match as much as possible the observational data with whatever you're doing. And this is the algorithm that I would like to suggest, which is, but in principle, that's what people would like to do. So what data assimilation is combining theoretical model with information from observations in order to obtain good approximation of the state of the physical system for certain future. So numerous applications are from meteorology, oceanography, oil industry, neuroscience, etc., etc. So this is the topic. So of course, where do you collect the data? You have weather stations all over the globe. You have airplanes. While the airplanes are really flying, they collect data. Okay, there's all kind of balloons and all kind of things. So there's data, a lot of data. So observational data we have a lot. So different approaches for data assimilation. I'm just giving you the names that people just because maybe heard them. There's some techniques called the nudging, Kalman filter, ensemble, Kalman filter. There's a lot of statistics involved in that in here. And I'm not going to talk about statistics. I'm going to talk about deterministic thing because I'm going to prove theorems. And later I can show you that I can do something with probability. Okay? But all these kind of like Kalman filter and ensemble, etc., they are statistical approach. Okay? And there's all kind of like something called the 3D VAR and 4D VAR, which are mostly statistical. Let me tell you that all these things here, there are no theorems about. And all these things, they basically, if you want to do theorem, you have to assume some Gaussianity and that the system is linear. But if there's something not linear as a paradigm of nonlinear is the weather condition. So basically, you know to prove a theorem for the linear, it says, okay, well, then I apply it here, that's it. So you assume Gaussianity and linearity, and then you can prove a theorem, and you're happy. But at the end of the day, it doesn't work. Okay? So, but this is basically what the restriction or the issues with all the other approaches. So feedback. I mean, the idea is coming from a work that I did with Azwani about feedback control, okay, a nudging approach, which is basically led to some work with Olson and myself, and with Azwani and Olson and myself. So I will tell you where the idea is coming from. So we combine the model measurements, adding feedback control terms to the equations. So my algorithm is I take the original equations, which I don't know their initial value. But what I will do, in some sense, I modify this equation by adding some nudging term. And I'll tell you why this logic term. I will give you a good reason behind it. And then I evaluate this new system with nudging term and show you that the solutions of this new model with the nudging term, which is like feedback control, is getting better and better and better approximation for my solution. Exponentially, in fact. Hence, if I take t large enough and stop, then the error between this exact solution, which is I don't know, and the model solution are very, very small. And then I can use this as initial value to go forward with the Navier-Stokes itself. Okay? So this is the idea behind this algorithm. So what happens is the following, that you have an original forecast, like say Navier-Stokes. I have a reference solution, but what's missing is the initial value. I'm just recapping what we have been saying. Okay? So I take this original model and I do an approximate model, namely original model plus feedback. Namely, I need to use the observation and use it somehow as a feedback control in order to get some new approximate solution, which is supposed to approximate the original solution, which I don't know. And then I integrate this model here, but I need initial value for the approximate solution. The initial value was missing here. Now, how to initialize that? The beauty of the theorem that we have, that I can initialize it arbitrary. No matter what I take, it goes to the exact solution. This is so nice. I take anything, it always goes to the same solution. And then, basically, the feedback control term forces, that's the whole idea, is the feedback control term forces the coarse spatial scales of the V, namely of the approximation, and the courses of the U, the measurements, it forces them to match. Why the coarse scales? Because when you do measurements, weather stations, you have one in Erlangen and one in Nürnberg, and one here. Of course, they are far apart. I collect data. This is the data I have. So I'd like to use this information. This is from the exact weather. And I'd like to use it and try to match it through nudging, and I'll tell you how to do it, with the evolving algorithmic solution. So the U and the V, namely the approximation, and the V, they are far. The observation and the solution V that I run, they are far apart. I would like to basically force at least the coarse mesh to match, because that's what I have. Okay, then why this will force define scales to match? Okay, and that's basically the idea behind the theorem. Okay, so I will try to force the coarse mesh to touch through nudging, and I will show you the proof that the whole solutions, all the scales, namely the difference, the norm between the two solutions, will exponentially come down. Okay, now this is basically the idea behind here. Where this idea came from? Well, you have to talk to the practitioners. This is coming from conventional theory of turbulence. Now, conventional theory of turbulence tells you that instabilities and turbulent flows occur at larger coarse scales. That's when the instability occurs, at large coarse scales. So the bad guys, the guys that I cannot control, the chaotic guys are the largest scales, the observational data. But now I'm connecting them, so I know explicitly the behavior of every bad guy. In some sense, can I use it in order to basically see what's happening? So what happens is that viscosity is stabilizing or dissipating the instabilities in the small scales. So the nonlinearity is destabilizing everybody, the small and the large. But the viscosity is very weak at the larger scales, the viscosity. It is very strong on the finer scales. It converts kinetic energy into heat. Therefore, it stabilizes the small scales. And what about the larger scales? They are basically keep moving crazily, and that's what makes the system chaotic. But there are finitely many such scales. There's a cut where the viscosity becomes too strong that you cannot really do. And therefore, there's a cut, there's finitely many degrees of freedom, in some sense, in turbulent flows. So conventional theory of turbulence asserts that turbulent flows possesses finite degrees of freedom. Now, is this a good result? Because turbulence is about long-term behavior, then I need to talk about long-term behavior of solutions. So I need to talk about the solution for a long time. If I'm going to talk about the Navier-Stokes, therefore, in order to talk about long-term behavior of the solution, I need to make sure that the solution lives long time. If you like to talk about retirement plan when you are 80, you have to live until 80. Otherwise, it doesn't make sense. It would be like basically just, just nonsense. Okay? So I need to guarantee that. Now we know that in Navier-Stokes, I don't have global existence in 3D. I have only short-term existence in 3D. But in 2D, I do have global existence. Therefore, if I would like to prove theorems, I should restrict myself to equations where I have global existence. And that's why most of the theorems that we have are for 2D. But if tomorrow somebody proves global regularity for 3D, if the drawer is full with papers, or maybe actually the computer is full with papers that only send print and submit, and then it goes to publication. So because the idea is the same. The idea is the same. All what I need is the solution to exist globally and bounds on the solution. Okay? And indeed, we apply this idea or this theory for other equations in fluid dynamics, which I know have global existence. So rigorous dynamical system approach is the approach that we have been using. And this has been, in some senses, long-term behavior of solutions of dissipative evolution equations is determined by finite number of degrees of freedom. I would like to capitalize on that, okay, in order to basically design my algorithm. So how this happens? So the very first work in this direction was due to Foch and project from 1967. Okay, well, they proved the following result, rigorous mathematically. This was the very first attempt to give rigorous result showing that turbulent flow are determined by finite parameters or by finite degrees of freedom. Now you should understand, I'm using words which I didn't define. Mathematics is all about definitions. Define a group, define a subgroup, define a normal group. It's all about definition. I didn't define what is a degree of freedom. This is concept that our next door neighbors, physicists and engineers use loosely to express themselves, but they don't have rigorous definition for it. Well, I mean, what's degree? Well, something that if I know, maybe then I have more understanding of the system. So we need to develop a framework of telling what are these degrees of freedom. And therefore, at the beginning, because of that coherence, I have to be very theoretical, namely not practical at the beginning. So I would like to identify this degrees of freedom, which is I cannot put my hands on them in practice. Okay? So the first result of Foch and Prodi we spoke about Fourier modes. What does it mean? If you take, say, solutions of the Navier-Stokes in a domain, and you expand the solution in terms of the eigenfunctions of the Stokes operator, or periodic in terms of sines and cosines. Now, what they say is the following. Suppose I have two solutions of the Navier-Stokes. So if you have two trajectories in the room here, and you look to their projection on the floor, and you see that the projection of the floor of these two trajectories, you only look at the projection, are getting closer. Can you say something about the two trajectories up there? No, two airplanes can be on top of each other. But if you take two solutions of Navier-Stokes in infinite dimensional space, and you look to the projection on the first, say, 1,000 Fourier modes, actually a large number depending on the viscosity, and you realize that, wait a minute, these two solutions, they are getting to collide in the projection. Because they are solutions of Navier-Stokes, the solutions are getting. Which means, if the low Fourier modes are getting closer, the full solutions are getting closer. This is counterintuitive for any random trajectories in the space, but because they are solutions of the Navier-Stokes, this is a theory. First, M Fourier modes, M large enough, depending on the physical parameter, determine the solution in unique fashion. I cannot have two solutions as the same low Fourier modes, but the infinite remaining are different. This means the low Fourier modes are determining the solution in unique fashion. That's exactly the result that I want. Okay? And this is the result of Foch and Prodi, and in which basically they prove let Pn be the orthogonal projection on the first n Fourier modes. N is large enough depending on the viscosity or depending on the physical parameters. Let U1 and U2 be two solutions of the 2D Navier-Stokes equation. Suppose Pn of U1 is Pn of U2 goes to 0 as time goes to infinity, then U1 minus U2 goes to 0. Therefore, the first N Fourier modes determine the solution, and this is finite. Exact the value of N we know in terms of the viscosity a priori.
Yeah. This is what Fourier and Prodi proved.
Yes. That's what 1967. Now, this is first result in this direction, and then there was a lot of work about trying to find explicit estimates in N in terms of Reynolds number. There was a lot of attempt, and the best result is by my former student Don Jones and myself, and we'll talk about it. But the problem here, if I tell you here is the temperature in this room, or the velocity in this room, and you give you equipment, huh? I tell you, can you measure for me the first 10 Fourier modes of the solution, of the temperature? Cannot measure. So therefore, it is mathematically it's a concept which is theoretically nice. It's a beautiful result, congratulations, but it's useless, you know, in that sense, practically. Why? Because I cannot measure Fourier mode. Yet it is basically shows that there is hope. And this was in 1967. And then the question became, can I become more practical? Can I generalize this to another concept? And then there was a result with Foyash and Timam about determining nodes, in which we, again, with Jones, we basically gave the best explicit estimate for that. So what is the spatial determining nodes? Aha! Imagine my first hand, whole hand, is a solution of the Navier-Stokes. Second hand is a solution of the Navier-Stokes. And suppose I know the nodal values, namely the solution at certain points. The tips of my fingers are getting closer. Then the result, if you have enough fingers or whatever, enough points, then the two hands should be close. This means the nodal values, there's finitely many nodal values, determine the solution in the fashion. Now, measuring the solutions at points is possible. And this is exactly what happens in the weather, because I have a weather station, so I know the solution at this point. Another weather station and the solution there. Now, I say the theorem states that the solutions at these model values, if I have enough of them, distributed in the world, determine the solution in a unique fashion. You see, this gives me hope. It determined the solution, and now this gives me hope. Okay, congratulations, you proved the theorem. They are determined uniquely the solution. Now, I challenge you to recover the solution from this information. If you're a numerical analyst, what did you do? What do numerical analysts do? I mean, from the days of Lagrange interpolant, whatever interpolant. You go interpolate and that's it. But this is ad hoc. What's interpolant? I give you the nodal values of the function, you do an interpolation, your favorite interpolant. But it's ad hoc. I don't take advantage of the fact that these are nodal values of solutions of Navier-Stokes. And that's exactly the idea of my algorithm, that because they are solutions of Navier-Stokes and they are interpolant, I would like, in some sense, to take advantage of that to recover the solution as accurate as possible. You see, this is the physics. I mean, I'm giving you motivation, physical motivation. I didn't prove this here, but while I understand the physics better, I can make maybe one more progress, one more step with the mathematics to motivate why it has a hope. Okay? Very good. So, we're doing okay. So, but once you talk about nodal values, how about local averages? Same story. So the same story we can do, you can determine the solution. But then after you do, now let us see. I try to connect this with numerical analysis. Let us see. If I tell you like some kind of like a question and inverse problem or a trivia. Fourier modes, local nodes, finite volumes. This is numerical analysis. This is like spectral method, finite differences, finite elements. So therefore, it seems that what's important is, whatever is your favorite projection method, if I know the resolution of the solution at the coarse mesh, whatever it is, it determines the solution in a unique fashion. And therefore, this has led us, together with Coburn, to talk about unified approach about the numerical interpolant. So if I have a coarse mesh interpolant of the solutions, it determines the solution in a unique fashion. So, how do I do, for example, volume? For example, if I take the domain, suppose I have the world, then I divide the world into small countries. what's important is the resolution of the country, namely the size of the country. And then at every country of size h, okay, diameter h, then I look for the local averages at every country. And then from this, I can have the characteristic function multiplied by the local average. This is an interpolant operator. This is one of those operator which is tells me that's how I represent the observations, because the observations are the phi ij's, or the phi j's average. And then from this, I can cook a function. Because if I know the phi bars, I know this function. This is basically observations. Now, or if you want, I can, now what happens is that, or what if I can do is I can talk about nodal values, namely I take nodes, and then instead of taking the averages here, I can take the nodal values as interpolant again, and this is IH of phi. So this is IH of phi and this IH of phi. Now notice that, for example, this IH of phi is enjoying the following properties, that it's approximation of identity. This is approximation theory. H of phi minus phi is less than H1 norm times phi and H2 norms of phi. Notice that the functions, because I'm in 2 dimensions, in order to make sense of the nodal values by solid embedding, has to be at least H2. Okay? So this is basically why I have this H2 approximation. These are approximation of identity. So the example is that I would like to talk about, as I said, is the Navier-Stokes. So here is the Navier-Stokes equation. I consider the Navier-Stokes equation. U is the velocity, P is the pressure, F is a given force. I'm forcing the Navier-Stokes. Usually it is coupled Navier-Stokes with the temperature, as in Rayleigh Binard or something like that. But suppose this is the dynamics of the Navier-Stokes equation. The unknown is the velocity and the pressure. Okay? So assume there is no model error. I'm assuming that this is perfect. As I said, I need to basically set the ground and do theorems under certain assumptions. Later, after I prove the first theorem, I can basically allow to myself the luxury of making mistakes and then estimate how far I am from reality with an uncertainty. Then I can, but at least let me assume first I live in an ideal world. That's what mathematicians, all the cows are spherical, you know, the spherical cows. Assume you have spherical cow. Okay? So I assume I have spherical cow. Assume everything, there is no errors here. The system representing the weather exactly. And let me see what kind of theorems I can prove. And later, the sphere, I can deform it. I start having like horns in the sphere. And then I start have tail in the sphere. And then I say, well, these are errors of certain orders. And then I can tell you, oh, the result is not exactly, it is within epsilon. So as I said, and also the other thing is that I have no error in the model, and I'm assuming that the measurements that I have, also there is no error. I have perfect equipment. Okay. So what happens in this case? So what's the approximate model? The approximate model says the following. This is the equation for V for the model, dV/dt. This is the Navier-Stokes. And then I'm having this ad hoc term here. This is an object term. What am I doing here? I am pushing the largest scales of my evolving model V to match the coarse scales of the observation of here. Why I want to do that? First look, if IH of U is equal to IH of V, then this is 0. Then V is solutions of Navier-Stokes. U is a solution of Navier-Stokes. If U solution Navier-Stokes and V solution Navier-Stokes, where the IH of U and the IH of V is the same, then U must be what? Equals to V. That's the theorem that we had earlier. That's the rationale. I push to match this with this, so the IH of U, the projection IH of V will start closer and closer. And hence the model for V is becoming closer and closer to become solution of Navier-Stokes. So that I can capitalize on that theorem to show that V and U becoming closer. End of story.
So let me ask you to make sure I understand. So you have a solution U of Navier-Stokes. You don't know the initial value, so you don't know what the solution U is.
I don't know U. I will cover.
Give me some projections of U.
IH of U, the observations.
Observations, which are finite number of them.
Points, yes.
Which are encoded in this
IH of U.
IH of U.
That's the
values on points or averages.
Yes,
or
exactly.
And then you say, now I solve this new equation.
Computer. On the computer.
Starting from which initial data?
Arbitrary.
Any. So I can take 0, for example.
Exactly.
and then you solve this V equation, and then you know in long time this V equation will be
minus u goes to 0 exponentially,
okay,
with rate proportional to beta, e to the minus beta theta. And therefore, because I didn't tell you what is beta, beta is a nudging parameter. Of course, because I converge with rate beta, then I want beta as large as possible. And if I take beta equals infinity, what happens? Instantaneously things happen. Okay? But there's no free lunch. So what happens while I'm stabilizing the large scales, IH is a rough interpolate. Therefore, while you're trying to do a good job, like you take a bear into a China store, and you ask the bear to put the vase here and the vase here. While the bear trying to do that, the tail will hit some nice thing and then will break. Then while you are trying to stabilize the larger scale, you disturb the finer scales. And the disturbance of the finer scales is multiplied by factor beta. But who is going to be in charge of stabilizing the finer scales? The viscosity. Therefore, but viscosity is given to me. Therefore, there's going to be fight between the beta and the viscosity and fine scales, namely the H. And therefore, this is the dichotomy. And that's why there is limitation. So it seems that I have to have a dichotomy between how fine is H, namely how many points I have. The more weather stations I have, the better. If I have infinity everywhere, then I have the solution. So therefore, there's a multiple between beta and H and nu. And this is a theorem. See, everything's like intuitive. Well, there's nothing, there's no magic here. Okay? That's why I cannot prove the millennium problem, because I don't have the ideas to do it. Okay? So this is the algorithm. And now, basically, how do you prove it? You look to W to be the difference. You discover that W is satisfying this relationship. You add and subtract beta W. Therefore, you get these terms. And now, you look to the following. This is the equation for W, the difference. You realize, aha, the blue terms are stabilizing terms. Laplacian W stabilizing the fine, but beta W stabilize everybody. And now, this is the nonlinear term, which is destabilizing everybody. But the nonlinear term, the viscosity stabilizes the finer scales from the red term, and the beta W's job is to stabilize, as I told you, the larger scales from the nonlinearity. And then I have this term here, because I said this is approximative identity, because this is proportional to H in some sense, multiplied by H, so by beta. Therefore, this is basically the destabilizing of the complement, namely of the finer scales. And this will be basically absorbed by the viscous term. And now the whole orchestra will play Mozart.
But you don't know U, right? And U appears in the equation.
Yes. But U is a solution of the linear structure, which is, I know this live in the attractor, therefore I know the bounded. In H1, H2 known for U a priori in terms
so
of the
you
viscosity.
need some a priori bound on
In the solution, because the weather has been evolved for many years, so it lives on the attractor, and that's why I know the solution in H1 norm is bounded by physical parameters, viscosity, Reynolds number, etc. This is given in advance, and therefore I can really give you explicit.
So you don't know what U is, but you have some a priori bound.
Of course. This is an assumption. And therefore I can give you exactly the value of beta and H, the dichotomy in which basically we have. And therefore I assume that this is an approximative identity. Okay? They have the H, but here's the L2 norm. And therefore, as I said, as an example for this IH, as I said, the lower bounds, or I can take the finite volumes, or I can take basically the nodal values. And these are the examples that I mentioned earlier. Okay. And now here's the theorem. If beta is large enough and H is small enough, depending on beta and nu, then U minus V is of the order to the minus delta. And how do I initialize V?
So first you need beta a bit large, right?
Oh yes, but then H is small. Or the most important is the product should be right. Because I want the beta as large as possible, but then restricted. So what happens usually in practice, the viscosity is given and the number of stations are given to me. because my beta is I design a computer algorithm. So I have the luxury in choosing beta. So you give me the H, you give me the nu. This is determines the beta here, so to satisfy that. And this is the beta which is gives me the size of it. Yes.
The O and equality is proportional to the initial error.
To the difference, yes. And basically, that's exactly the point. Because the initial data of the solution, I don't know it, but I know it is in a big ball, depends on its number. And V initial data is 0, for example. Therefore, I know the difference of the initial data. And then I can okay? So now, once you prove a theorem for one equation, then you can basically start practicing on other equations which are of the same type. So then we can do the same for other models like 3D Navier-Stokes alpha, in which we know global existence and uniqueness for this particular model. And then one can talk about Froschheimer extended Darcy law, and then we can do also for 2D SQG equation, you know, many equations. So partial. Now, this is the first result. Now, as I said, in the climate or in the weather, usually the atmosphere is coupled with the temperature. And therefore, the state variables are the velocity and the temperature. I showed you the theorem for the velocity field, Navier-Stokes. But if I have also temperature, therefore any measurements of the velocity and of the temperature, like I already done, you have the same theorem. But then you start basically acting smart, and you ask the question, listen, do I really need to measure all the state variables, or do some of the state variables follow? Okay. Now, of course, if I'm doing temperature and velocity, if I tell you basically, can you please, sir, measure for me the velocity at this point, at this point, at this point, I have to train. I have to bring special devices, special equipment to measure velocity at every point. But I tell you, sir, can you measure the temperature here or here or here? You can bring 14 years old kid to stick the thermometer and read it. So if I can measure the temperature alone without the velocity and I can really determine everybody, wow, it is so cheap and so practical. Fortunately, this is not correct. However, we have a theorem which says that it's enough to have measurements of one component of the velocity. And the other component follows slave because of the incompressibility, and the temperature also slave in that sense. And this is a result with Asil, with Asil Farhat and Mike Jolie. So to this, it's enough to have one component of the velocity. This reduces the system, yes.
But this is for 2D. If you have 3D, you probably need 2D.
I don't have theorem for 3D because I don't have global existence.
If you assume that you have.
Then yes, then two components. Okay? And the same, you can talk about 3D planetary geostrophic models. Actually, for planetary geostrophic models is enough the temperature. It's a different model. This is in geophysics. So what happens is that I cannot have a theorem in abstract, in a generality. You have to take case by case because every equation has its own features. You have to take advantage of the features and do it. So planetary geostrophic model, which is a climate model, then you can do it with the temperature. And this has been conjectured by Charney, and basically we proved that basically the temperature of the climate in some sense determine uniquely its behavior or something like that. Again, this is basically the result that we have. In 3D Bernard, in porous medium, we have the same thing, the temperature is enough. And 3D Leray alpha, we have two components is enough, which is related to your equation. There are some other results in which basically which norms are using. I proved that basically conversion is 2, but you can conversion H1. And then basically depends on the regularity, people can do better results. There's a whole, after you know what result, then there is a lot of work that people have been doing in which basically people have been showing conversions for different models. And actually they start showing in some sense also that you can play with the algorithm to show that the solution is converging maybe faster and faster. Remember, I chose the lodging to be linear. Beta. But why it should be like that? Okay? Well, this is basically the most intuitive. This is the first. But now we have an improvement for that. And let me tell you that, again, as I said, I'm a simple person. Let me just tell you what's the idea. And once you have the idea, then you can see what's happening really to this equation. So suppose you have the equation x dot equals minus beta x. Then the solution converging exponentially e to the minus beta. And x goes to 0. This is the error. The larger the beta, the better it is. Now, I would like to basically make it adaptive. So what if I look at this kind of like, bear with me, minus x divided by x to the power gamma. This is converging to 0 much faster than the upper one when gamma is small. Because the rate is basically like 1 over x1 is gamma. Okay? So indeed, therefore, we can take combination then. So when you are large, you converge exponentially, and when you become close, you are super convergent. And that's what we should. But this is becoming like cheating. This is becoming like basically, I would say, cheap tricks, plum-ups. Okay, it's an engineering trick. But nonetheless, they really make a big difference about what's happening in this. So now I told you if you have continuous in data, what happens if you have discrete measurements? So if you have discrete in space and discrete in time, you have to basically discrete in time, but you have to take it enough. I cannot take one measurement and like basically like you're living in some kind of part of the world, you know, you take one measurements and then go for lunch or whatever and go for dinner, and the next day you can take the next measurements. I mean, there's memories. You have to take it frequently enough. So therefore, suppose you have measurements and suppose there's error in the measurements, eta n. Okay, what happens in this case? So this is a result that we have in the approximate model. Then I do again the nudging, but I interpolate in time as well. Okay, so take the measurements at time, and then with the error, I don't have IH of u. I have the sum of them. I cannot decompose it. I don't know how to decompose it. So when I take such a model, one can show that again, that in this case, if beta large enough, blah, blah, the lim sup is less than the error E in the measurements. And when E is 0, the error is exponential. So in some sense, if you have error in the measurements, then you expect that you get the answer. It decays exponentially fast, but within a tolerance, which is the error in the measurements. Okay, this is the result. So what about the numerical approximation? So in practice, numerical models can only compute finite dimensional approximations. Okay, the goal is to obtain analytical estimates of the error between the numerical approximation of V, the algorithm, and the reference solution U. U is the exact solution, but V is algorithm in the computer, so I can really approximate. So suppose I look into this, the equation of V, this is the equation for V, and suppose I do, say, Galerkin approximation based on eigenvalues of the Stokes operator. Okay, and now the Galerkin spectral method for V is satisfying this system of ODE when Pn is a projection on n eigenfunctions of the Stokes operators. This is the Pn. So IH of U is given, this is the observation, but I take IH of Vn. This is the algorithm that I compute. So this is the solution U, this is the solution V, okay? This is Vn, namely the solution of the Galerkin, and this is Pn of V. And this is on the finite dimensional space. Now, let me draw your attention to something maybe you already observed, or maybe you didn't observe. And this was a shock for us. What is this observation? Extremely important. U solves Navier Stokes. I would like to approximate. U itself is a chaotic solution, which is terminals. What did I prove? I B with any initial data converge to the same unit. If I perturb the initial data for V, what happens? I converge to the same unit. In other words, V is not sensitive to the initial value. And this is, in some sense, the curse of numerical analysis of chaotic systems. That I cannot integrate for a long time. Here, this theorem tells me, no, don't worry about V. Whatever you compute with V, you always go to the same thing. Don't worry about errors. In other words, the errors in computing V are really not expanding in time. It's stable. Hence, you expect, if you adapt Galerkin approximation for V, you approximate error with U uniformly in time. This is a given. This is surprise. But why? Because the chaos is coming from the larger scales, and the larger scales are supplied to me. Therefore, I don't have basically this particular. So what happens is the following. So if Qn is the complement, but we can show that Vn minus U is converging exponentially fast. Theta is smaller than 1, plus an error, which is 1 over lambda n. Lambda n is the eigenvalues. How many eigenvalues? Lambda n, think about lambda n is like 1 over delta x squared in final differences. So therefore, one can show that Vn, namely the Galerkin solution minus U, is, as t is large enough, is basically like delta x squared. Uniform delta. And this is basically the numerical version of this particular system. Okay? So now, after we know that the Galerkin is doing a good job, there was a work which was did in the 90s with the Bosco Arquia with the Novo called post-processing, about post-processing Galerkin. And what is the post-processing Galerkin idea? The post-processing Galerkin idea, it states the following. Let me just explain it in a couple of words, and then I basically adapt it in my context. It says the following. It says that if you give me, suppose I have a solution V of equation like Navier-Stokes, like in my algorithm. And then I do Galerkin approximation minus Vn. Then one can show that this is less or equal than constant divided by lambda n plus 1. And lambda n is like delta x squared. This is the error. This is here. Now, what one observes the following. If I take Pn of V minus Vn, what's Pn of V? The projection on the first n Fourier modes minus Vn minus the Galerkin. So here is the space of solution. Here is V, here is Vn. This is the solution of Galerkin. This is V, and I project here. This is Pn of V. It turns to be that this distance is much smaller than this. Much smaller than V minus Vn. Therefore, most of the error committed in Galerkin is by ignoring the high frequencies. The question, can you post-process and recover some of the high frequencies through some technique to basically recover error, to get an error of this order, small enough? This is what happens. This is of the order like lambda n plus 1 minus 3 halves, while this is lambda n minus 1. This is much smaller. And so the post-processing technique is, we are able to do it. And therefore, if you do post-processing, you don't only get good approximation uniformly in time, but even you get better approximation in this case. How much time do you have?
What time do you have? 4. So, yeah, we have to leave the room in 9 minutes.
Okay, very good. So this is basically showing numerically, after we design the algorithm, that numerically you can basically also get an algorithm in which more efficient in order to compute the Vn. So of course, I will let me just go into some of the results that we know about the numerics and about computations. Okay. So the post-processing Galerkin, we basically you show that you get better approximation, as I said, like lambda n to the 3 halves, and instead of like lambda n to the minus 1, as before. This is for this algorithm. Now, then also you can discretize the time if you like, and then you can show that the discrete and space of time, the full discretization, is also converging, and so on and so forth. Let me just recent extension and full discretizations. As I said, so with IBDAH we have like full discretization in space and time. Similar results are for a fully discrete system, as I say. Now, Garcia and Novo, we did it for the finite elements because I showed to you the theorems in Galerkin based on eigenfunctions of the Stokes operator, which is many people will criticize that, says nobody uses this in practice, but in really complex geometry, people use finite elements, they only have theorems for finite elements, but it's easier to do the Galerkin to explain ideas. Similar results are for finite elements divergence. So let me skip this, if you don't mind. So implementation, together with Haydn and Olson, we implemented the Navier-Stokes when the observations are the low Fourier modes. And then with Schilling, we basically also did the observation. We did the same with the general situation. So that's the recent advancements. This topic, determining forms, is a lecture by itself. Okay, it's a lecture by itself. And let me tell you what's the essence of this lecture. Based on this algorithm, which is related now to machine learning. We call machine learning, so it's related to machine learning. Based on this theorem, I can show if you give me the history of the solution, history of the observation, the solution on the larger scales, trajectory, then I can use this algorithm to show you there is a unique solution corresponding to that. You give me trajectory, but finite dimensional space. I give you trajectory in infinite dimensional space. Trajectory, 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 trajectory. And therefore, this is defines a map. That's what mathematicians do. So a map from this space of trajectories, which is Banach space, into space of trajectories, which is of solutions in the Navier-Stokes. And then what do mathematicians do when you topologists, what do you do when you give them a map? They would like to investigate its regularity. This map is Lipschitz. Actually, even more. It is Frechet differentiable. Okay? Now, if I can put my hand on this map, wait a minute. This means, I know explicitly this map. You give an observation, I plug in, I get the solution. I don't need to do anything. If I put my hands on this map, I know it exists and it's beautiful and nice. I know there's a law. The law gives you from observation, solution, observation, input, output, input, output. Put my hands, then you give me any trajectories, any observation, I plug them in, I get the solution. What do you do in machine learning? You're trying to get this map. So I can train, I can get approximately this map, and I'm done. So we have machine learning machine for this. Once you have that, what you can do, now you start putting Christmas tree, bells and whistles, beep, 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 you know, whatever you want. For example, I have uncertainty in the model, yeah? I said the model is perfect, I could be. But how do I really add uncertainty to the model? You know, nobody knows how to put uncertainty anymore. People put like random force there, nonsense. What we suggest, once I get trained this machine and I got the weights are for the exact perfect model. So I can basically make them random. I can put stochastic weights, which is manifesting uncertainty in the model. And so on and so forth. And this is basically part of the recent advancement. I stop here. We did some computations. We don't have time to show you the video of the computations. It's surprising that the theorem says you need so many modes in order to do the theorem. Like says I need like to have 5,000 measurements, whatever. This algorithm in practice says 49 is enough. You don't need 5,000 or 50,000. And this is the power of like, in some sense, that things which is to prove theorems you need demand more, but in practice you need this. Thank you very much. I stop here.
Thank you.